Hey everybody, welcome back. We're going to be picking up where we left off last time. And so we're going to be working on question number 5 of the fall 2021 exam or midterm exam. So number 5 is all about translating C code to ARM code. And so this question is made to evaluate your understanding of the ARM ISA, as well as memory accesses, as well as I think there's a little bit of struct alignment in here. But it's a pretty holistic question. So we're going to go ahead and get started. So I think the first step that I tend to take is kind of identify where the first line of code that we have to translate is. So up here, we're just defining a data structure, but we're not actually performing any sort of operations. So we don't need to worry about translating that, although it will be relevant later. So looks like the first line of code that we have to execute is here. We're assigning a variable good count to 0. So it says, the question says the return value is going to be in register 2. And so if we look at our return value, returning good count. So that probably means that good count is this value that's referenced in register 2. So the value that we want to assign to it in this case is going to be 0. So we can go ahead and fill that value in. So that assigns good count to 0. So we can annotate that and write that value, that variable is in register 2. So then we have an instructor provided line, which tells us that we're going to assign register 3 to 0. So if I scan the code really quickly, we see that the next assignment happens at the initialization of this loop. We assign the variable I to 0. So I think it's fair to say, or it's a reasonable assumption to say that I is the variable that's associated with register 3. Awesome. So then we start what's considered like the body of the loop, and the label kind of points me towards that. And the first thing we do is we perform a comparison between register 3, which we know contains I, and the immediate value 512. And if they're equal, we need to perform some sort of branch operation. So let's think about it. So if I were equal to 512, we would be done. That's kind of like our end condition for our loop. And so we're going to want to jump all the way down here, right? And at that point, assuming that register 2 contains our good count value, we don't really need to do anything. And so we can jump all the way to the end of this function. Awesome. So then once we've performed our branch, if we need to, we can go ahead and start executing the body of this loop. And so the first step in executing the body of this loop is accessing this variable right here. And so it's a little bit tricky, but we need to somehow access the ith element of data, and then we need to access the numpence attribute within it. So data looks like, from our definition, it looks like an array of pencil packs, right? So if I wanted to access the ith element, right, I can't just add I to the address because that would give me, let's say I wanted to access the 5th element in this array, that would just give me 5 bytes ahead. Whereas because we are storing an array of pencil packs, we need to consider the size of pencil packs. So if the size was like 10 bytes, we would want to go 50 bytes, right, forward. And that would tell us where that particular struct starts. So the first step is to kind of evaluate how big this struct is. So the size of this struct is going to be, so if we add it up, we're going to get 28 bytes. However, going back to what we saw in number 2, we need to worry about struct alignment. And so since the biggest primitive in here is a 8-byte integer, we need to align it such that the size of the pencil pack is a multiple of 8. And so the size of this struct is actually going to be 32 bytes wide. So essentially what we need to do is the first step we need to do in accessing this is multiply I by 32 so that we can kind of translate the number, the integer representation into an address offset. So looks like we have a blank line here. So if I wanted to multiply something by 32, it's really convenient because 32 is going to be a multiple of 2. And so going back to what we discussed earlier in this class, we can perform multiplication by bit shifting, and particularly bit shifting left. And so we can perform a logical shift left. Our destination is going to be register 4, but the value that I want to multiply is I, which is located in register 3. So that's going to belong there. And the amount that I want to shift it by is the log is 2 of 32. And that's going to give us 5. So if we bit shift something left by 5 bits, we're going to essentially multiply it by 32. Awesome. Apologize for my handwriting. So now we've multiplied I and we've converted it to an address offset. Let's go ahead and get the starting address for that particular struct in the array. So the way we can do this is essentially take the value that we just computed, which is located in register 4, and we can add the starting address of the entire data array. So that's going to be located in, I think it says register X0. So register 0. Awesome. So now we have successfully found the address that we've successfully founded the address that data at I begins at. However, we don't just want that. We want to find the address that the num pencils attribute is stored at. And so we need to figure out where this begins and then load that, right? Within a pencil pack, right, structure, remember this 8-byte primitive is the word I was looking for, sorry. But this 8-byte primitive needs to start at a multiple of 8, right? So it's not going to start at 20 bytes into the struct. It's going to start 24 bytes into the struct, right? So essentially, we want to load the value at register 4 with an offset of 24. And so we can do that by performing an elder instruction here. And then we can have an offset of 24, and my base address would be in register 4. So now we've successfully loaded data I's num pencil attribute. So then we want to compare that value. It looks like we want to check if it's less than 20. So we can compare register 5, which is where we have our value, and we can compare that to 20. Awesome. So there's a number of cases, right? So we could check if it's less than 20, right? And we're going to perform this code if it's less than 20. We could check if it's greater than 20, and we could perform this code if it's greater than 20. Or the last case is that I'm going to check if it is equal to, right? Because that's the only third possible case. So I have equality, I have less than, and I have equal to. So I'm looking at the starter code that we've been giving in the ARM, and we see that we have bigger and smaller labels. And so we can take advantage of this by just kind of doing b dot greater than, right? So if it's greater than 20, then we can jump to our bigger label. If it's less than, we can jump to our smaller label. And if not, right, so this is kind of going to be like our implied equals label. Awesome. So if it's equal, all we need to do is execute good count, right? We need to add 1 to good count. So good count, remember, is stored in register 2. So our destination is going to be register 2. And since we're incrementing it, it's our value that we're going to be adding. 1, 2 is also going to be register 2. So this will essentially increment good count. So once we've executed that iteration, I want to probably jump back up to the top of the for loop, right? And so I can just do branch to loop. Or actually, this is tricky. If I just branch the loop right now, we'd see that we'd never iterate I, which is bad because we just end up in an infinite loop, right? So the only part of code that I see that could potentially increment I is this right here, the for end. So instead of branching to loop, I'm going to branch to for end. If I just like kind of glance at this code so far, it looks like this is going to be where I perform plus plus I. In fact, we can just go ahead and do that right now, just while I remember, because that code is going to be very similar. So I stored in register 3, and the value I want to add is 1. And once I've added I 1 to I can jump back to the beginning of my loop. So that'll prevent us from infinite looping. Awesome. So now we have performed the equals. If it's bigger, so that's going to be this code right here, right? So all I want to do is re-access that value that we got earlier, and we want to divide it by 2. So let's think about, so we know that this value is stored in register 5. And so let's think about how we could first divide that, right? We're not going to worry about the assignment initially. How could we divide that value by 2? Well, we could, instead of left shifting, we could right shift. So instead of taking the log of 32 like we did earlier, we want to divide by 2. So we're going to take the log base 2 of 2, and that's going to give us 1. And so we're going to want to shift register 5 over by 1. And so that will calculate the value. However, not only do we need to divide it by 2, we need to reassign that value to memory. And so we need to perform a store instruction, right? So that's probably going to be what belongs here. It's essentially going to be the same way we accessed it up here. The base address is going to be stored in register 4. Right? That gives us data at I, and we want to assign that to the num pencils attribute. So that's going to be 24 offset. Awesome. So now we've performed this operation, and similarly, I just want to branch down to the for end so that we can iterate I and then jump back to the top of the loop. Then we're going to do this smaller. So this one looks a little bit trickier, but I'm sure we can handle it. So first, it looks like we have an if, another conditional. I'm going to go ahead and see if I can't erase some of this stuff. Never mind. Okay, so next what we're going to do is we're going to try to calculate. It looks like it's checking, it's performing the modulo of with respect to 2. So essentially it's checking if it's even or not. Right? Because if I take the modulo of 2 and it's 0, it's going to tell me it's even. If I do the modulo with 2 and it gives me 1, it's going to be an odd. Okay, so how do I perform a modulo operation? So this is probably something you might have seen earlier in this class. The way you can do that is performing an and I instruction. Essentially, we only want to look at the last bit of data at I.numpence, right? So the way I can do that is by bit masking it with just the last bit as a 1. And so if I bit mask it with a 1, right? And it looks like the destination here is going to be register 7. That'll give us whether that'll give us a 0 or a 1. So then I probably want to compare it to 0. That's probably what this next line is. And it's going to be compare immediate, because that second value is immediate. And if it is equal to a 0, right, then it means it must be even. So I can branch to my even label that's down here. If not, that means this is odd. So if it's odd, right, then I'm going to want to just add 8, right? So I can perform an add I instruction, and I want to take the value that's currently in register 5 and just add 8 to it. And so that'll calculate plus 8, and then we're going to store that in memory. It looks like that's already written for us. So once I've executed that, again, I'm just going to jump to the end of my for loop where I iterate I and jump, and then from there it'll restart the loop. Okay, so however, if it's even, it looks like we want to multiply by 4. And so the way that we multiply by 4, similar to the way we multiplied by 32 earlier, is we're going to do a logical left shift. But this time, the number of bits we're going to want to shift over is going to be the log of 4, which is going to be 2. So you're going to want to shift over 2 bits. So now that we've performed a logical shift and multiplied by 4, we're going to want to reassign that. And it's going to kind of mirror what we were doing earlier. We're going to do a store instruction. And our destination is going to be register 5. And our base address is going to be offset, really register 4, and our offset's 24. So awesome. So looks like we have successfully completed that question. This should be correct if I'm not wrong, but yep, awesome. So hopefully that was helpful. Next time we're going to be looking at question number 6, which is all about a single cycle processor. Awesome.